Welcome to a lesson with Dr. Powell. Let's take a look at a way that we can rewrite an integral over a region in x and y coordinates as an integral over a region with the r and theta coordinates. Now, when we think about r and theta coordinates, we think of dr times d theta. That's like having a dr and d theta mapped out rectangularly like this. And so dr times d theta would be equal to an area. How is an area like this, of this rectangle with r and theta, related to an area over here in x and y coordinates? We get the answer with the derivative of the transformation that takes us from polar coordinates to Cartesian coordinates. The derivative is right here, the first derivative, where we have two outputs and two inputs. So we get a 2 by 2 matrix. Remember, it's a rule that takes us from run to rise. So here's our run here in terms of dr and d theta, and we output a rise in terms of dx and dy. All right, so let's kind of analyze this situation for a minute. What if we were to look at this rectangle, and let's consider just dr, this direction. That's kind of like inputting dr and 0. What do we output? Well, if you run through this matrix multiplication, we actually get what I have up here, but I factored out the dr as a scalar times cosine sine theta. Similarly, if we were to look at this arrow that goes up here, that would be just like doing 0 d theta. And the output is actually this vector right here. So this is the rise. So we actually get, so this vector right here has a rise of this vector, and this one has a rise of that vector right there in x and y coordinates. This tells us that this rectangle turns into this parallelogram over here in xy coordinates if we're computing area. That's kind of how it maps over. Now, what is the area of this parallelogram compared to the area of this one? I mean, what is this area? And can we write it in terms of dr and d theta, especially since we have dr and d theta present here? Let's think about what this is. This is nothing more than taking this matrix and multiplying this particular column by dr and dr, and taking this column and multiplying it by d theta. So we get, so in some sense, maybe we can just write this in for a second, there, and a d theta. Now, if we were to take the determinant of this matrix, what does that mean? Like crossing it this way and that way. Hey, that's like the same thing as taking like a cross product, which would compute area of a parallelogram. So that's what we're going to do to compute this area. We'll take a cross product, which is nothing more than just taking this determinant right here. And so in doing so, we'll notice that in each term we have a dr and d theta. Let's just factor that out of everything. So if we factor out a dr and a d theta, and computing the determinant, we end up getting r times cosine squared and a minus r times sine squared. So we end up actually getting r times 1, or just r. So this is what we get. Dr d theta in the coordinate system over here, a rectangle over here, actually turns into a parallelogram, which has this area right here. So if we want to rewrite something in terms of x and y, we have to realize that if we have a rectangle in x and y over here, which is a parallelogram of sorts, but we were to convert it over to something in terms of dr and d theta, we have to realize that to move back to this is we have to divide by r to get back here. But if we start here, we have to multiply by r to get over here. So if we want to actually back up and rewrite things in terms of dr and d theta, But we want this to express an area over in the XY coordinate system. To make that expression, you have to multiply this by r to make that expression. So if we express a region in terms of r and theta coordinates instead of x and y coordinates, we also have to make this adjustment right here, r dr d theta. It's kind of in some sense like a substitution, if you will, like a trigonometric substitution or something, where you have like an x and you like your dx, and you rewrite your dx in terms of d theta using something like this. It's the same idea for like a trigonometric substitution, but we're just having two coordinates at once. So we have this 2 by 2 determinant matrix that we're using, but we're using the determinant to discuss the area difference and ratio between them. And in particular, whenever we do something like this, we would take the absolute value of this determinant, especially if we're just concerned with positive values of area. Thanks for watching.